Section 8.3, complex numbers in polar form. All right, let's look at a complex number. A complex number has a form a plus bi. In this book, they choose to call it z, a complex number. All right, so what is a complex number? It might be 3 plus 4i, okay? Where a is 3 in this case, and 4 is your b, okay? They call a the real part, and they call b the imaginary part, all right? Up till now, you've been dealing with complex numbers, actually. Let's say the number 5, okay? It's actually a complex number because it can be written as a plus bi. 5 can be written as 5 plus 0i, okay? So a happens to be 5, and b happens to be 0, okay? Also, square root of 2 is actually a complex number because it can be written as the square root of 2 plus 0i. And that's a plus bi, where b is 0. Also, say you have a number that is negative 4i. That's a complex number as well because it can be written as 0 plus a negative 4i. Now your a in this case would be 0, your b in this case would be negative 4, okay? So complex numbers are just a bigger number system that has real numbers and it has imaginary numbers in it, okay? And I is just an imaginary unit, which is the square root of negative 1. All right, so what we're going to do now, instead of looking at a coordinate plane with an x-axis and a y-axis, we're going to look at a real axis being this right here. Our horizontal axis is my real axis, and my vertical axis is going to be my imaginary axis, okay? And they want us to graph some of these numbers in a complex plane. Like, let's say I want to graph this number negative 2 minus I, okay? So this is in the form a plus bi, actually, okay? And a is your real part. So on your real axis, you want to go to negative 2. So in your real axis, you go to negative 2 right here. And then what's your imaginary part is negative 1. Your b part is negative 1. So in your imaginary axis, you go down to negative 1. And this would be the point like negative 2 minus I. How about this number, this complex number? Z is equal to negative 4. Isn't that the same thing as negative 4 plus 0i? So negative 4 is your real part. So you go on your real axis to negative 4, and then 0i. So for your imaginary axis, you go to 0. So that would put you right here on this axis, and that's negative 4 plus 0i. And what about 3i? 3i can be rewritten as 0 plus 3i. So a plus bi. So your real part is what, 0, and your imaginary part is 3. So on your real axis right here, go to 0. And on your imaginary axis, you go to 3. 1, 2, 3. And that puts you on this axis, and that's what? 3i right there. Or 0 plus 3i, whichever way you want to say it. All right, so we know how to graph these now in the in the complex plane, okay? Now let's look at what's next in your notes. It says absolute value of a complex number. Absolute value of a complex number. Then it says if z is equal to a plus bi is a complex number, then the absolute value of z, also called the modulus or magnitude of z, is given by. They're saying this, the modulus or the absolute value of z is given by the square root of a squared plus b squared, okay? Now what are they saying here? They're basically saying, suppose I have a real axis and an imaginary axis here, and then I have some point over here, z is equal to a plus bi. What they're basically saying is this point right here, a plus bi, means I go to, or I go out right here, 8 units on my real axis, and I go up b units on my imaginary axis, okay? So in other words, we could look at this instead of z is equal to a plus bi, I could look at it as like an ordered pair, a comma b like this. And what they're talking about, the modulus or the magnitude, or what else do they call it? The absolute value. We're looking at the distance from this origin right here to this point AB. So how do you find that? If you use either Pythagorean theorem or the distance formula, is going to be magnitude of z is equal to the square root of a squared plus b squared. All right, so let's use this. Or next example, what does it tell us to do? It tells us find the modulus of a complex number. All right, so for part A, they give us a complex number. Z is equal to negative 14 plus 6i, right? If I want to find the magnitude or the modulus, how do I do that? I use that formula, square root of a squared plus b squared. Now what is a in this case? Remember, this is the form a plus bi. I'm going to make sure I'm still on the screen here. Yeah. So a is negative 14 and b is 6. So this will be the square root of negative 14 squared plus 6 squared, right? What is that? Square root of 196 plus 36, I believe. Oh, what does that give me? 230 what? 32 maybe? 232? All right, now let's take the square root of 232. Well, the square root of 232 is not exact, but it could be broken down into 4 times, I think it's 58 here. Let me check my notes. Yeah, 4 times 58. Now 4 is a perfect square, so that comes to the outside as 2, and 58 stays under the radical. So there is my modulus of that complex number. Now we're doing this because we're getting the bigger things here, okay? That's why we're doing these simple calculations, because it's going to be involved in other problems later on in this section. How about z? Z is equal to negative 1 plus the square root of 3 over 3 times I. All right, so what do they want? They want the modulus. So that's equal to the square root of a squared, which is negative 1 squared, plus b squared, which is square root of 3 over 3 squared, right? So what does this give me? That gives me 1 plus, what happens when you square the square root of 3? You square it, you just get 3, right? What happens when you square the denominator? You get 9. Well, wouldn't that be the same thing as the square root of 1 plus 1/3? What's 1 plus 1/3? Well, that's 3/3 plus 1/3 is what, 4/3? Or plus 1/3, I should say. Isn't this the same thing as the square root of my numerator over the square root of my denominator? Square root of 4 is 2. I can't take the square root of 3, so it stays like that, right? Now, if we rationalize our denominator, we'll multiply the top and the bottom by the square root of 3. And what does that give me? 2 square roots of 3 over 3 is the modulus of this complex number. All right. I'm going to skip the other part. I was just showing you how things were derived there. Let's go on to page 3 in our notes. Page 3 in our notes. It says polar form of a complex number. And it says the polar form. What are we looking at when we're looking at polar form? It's kind of the same thing we were looking at before. Whenever we had the graph points in here and so forth. That was polar form of real numbers that we dealt with before. Okay? Now we're going to look at putting these complex numbers, these numbers with eyes on them. We're going to look at putting them in polar form. Now, why would I want to complicate things and put those in polar form? Well, I'm so glad you asked. The reason why is because operations on them like squaring them, cubing them, raising them to the fifth and stuff like that. It makes it much easier if they're in polar form, much easier and quicker. All right, so they say the polar form, or what they call the trigonometric form of a complex number, z is equal to a plus bi, z is equal to r times the cosine of theta plus I times the sine of theta. Okay? So normally what do we have? Normally we have in rectangular form, z is equal to a plus bi, but sometimes we want to convert them to polar form, so we want to put them in r times the cosine of theta plus I sine of theta, okay? All right, they say where a, I'll tell you what, let's just go ahead and derive this. Why not? Makes it easier to understand. Let's suppose I have z is equal to a plus bi. And I want to go to z is equal to r times the cosine of theta plus I sine of theta, okay? All right, well, think about your real axis and think about your imaginary axis here, okay? And think about some number, a comma b, okay, out here. Or z is equal to a plus bi. All right, we got this part right here, okay? Now, if I plot that point, how many or how far am I displaced in this direction? A units, right? How about in this direction? How far is this point displaced from my x-axis? B units, right? And we can make a right triangle right there. And we could say that this distance right here is like my radius, so we call it r, and that's equal to the square root of x squared plus y squared. And let's look at some angle theta right here, okay? All right, so if we look at this triangle right here, what would you say the cosine of theta is? Tell you what, for right now, let's just call this r, just to make it easier to look at, okay? Let's just call that r right now, make it easier to look at. What would you say cosine of theta is? A over r? What would you say your sine of theta is? Angle theta, sine is b over r? And we actually saw this type of thing before. What happens if we multiply both sides by r? We have r cosine of theta is equal to a. Or I could say a is equal to r times cosine of theta, right? Over here, if I multiply both sides by r, I have r times sine of theta is equal to b. Or b is equal to r times sine of theta. All right? Let's see. So what am I doing? I'm saying, how do I take a complex number in this form, z is equal to a plus bi, and convert it to this form? Well, what is a? We just said a is r cosine of theta, right? So instead of a right there, I could write r times cosine of theta. Plus, what is b? B we just said was r times sine of theta. R times sine of theta. Times I, right? Because it's bi. Well, what do I get if I factor an r out of both of these? If I factor an r out, I'm left with a cosine of theta plus sine of theta times I. Or I couldn't actually write this as r times the cosine of theta plus, and commute these two around, I times the sine of theta? Sure can. So that's where this comes from. That's exactly where that comes from. All right. Now, the way you find that r is like we had up there earlier. R is the square root of x squared plus y squared you may need to use here. And then, or actually in this case, it's not x, y, it's what, a and b, because my order pair is ab, not xy. A squared plus b squared under square root. And tangent of theta is equal to b over a as long as a is not equal to 0, okay? We're going to use all that stuff there. All right, let's look at our next example. Our next example here. What does our next example read? Write the complex number in polar form. Write the complex number in polar form where theta is between 0 and 2 pi radians, okay? And then they give me for part A, 2 minus 2 square roots of 3 times I. So I want to write that number, which is a complex number, in polar form. So how do I write this number in polar form? Or let's think about where I'm going. Where am I heading? I want to head this direction. I want R times the cosine of theta plus I times the sine of theta, okay? That's the form I want to convert it into. Well, let's find R first of all, okay? So R is the square root of a squared plus b squared, we said. So that means R is equal to the square root of, what's A? 2, let's square it, plus B squared we have here, right? What's B? What's the part that's being multiplied by I? Negative 2 square roots of 3. So R will be equal to 4 plus, if I square 2, I get 4, right? If I square the square root of 3, I get 3. So what does this give me? The square root of 16? 4 times 3 is 12, plus 4 is what? 16? So R is equal to 4. So I know this part. I know that R value is 4. Now I need to come up with a theta here so I can plug in cosine of theta, sine theta. So let's see what theta is. So to find theta, let's graph this complex number, okay? Let's graph it in the rectangular plane, okay? Remember, this is the real axis and this is the imaginary axis, right? 2 minus 2 square roots of 3. 2 minus 2 square roots of 3 is somewhere over here, right? All right, I just found this R just a minute ago. Now I need to find theta. So I'm going to use the fact that the tangent of theta is equal to b over a, okay? So the tangent of theta is going to equal to, what's my b value again? Negative 2 square roots of 3 over a. What is my a value again? 2. So that's the tangent of theta is equal to negative square root of 3 over 1, right? Or I could say negative square root of 3. Let me think about that. What angle is that then? Theta is equal to, where do I have a tangent that is a square root of 3? I have a tangent that's a square root of 3 at what? Let's see, pi over 3, right? Pi over 3 radians. And technically it's a negative. Now, what did I just found whenever I found the theta value right here? What I actually found now was the acute angle right here. I found that to be pi over 3 right there. And that's really my reference angle. Theta prime is equal to pi over 3. So really what I found here was theta prime, theta prime, theta prime. And how do I know that? Because they tell me that my theta value needs to be between what? 0 and 2 pi. So it can't be negative pi over 3. So my actual theta value is going to be this angle here. So how do I find that theta value? How do I find this value right here? I say 2 pi minus pi over 3. So theta is going to be 2 pi, which is all the way around, right? Then back off. Pi over 3. Well, that's what? 6 pi over 3 minus pi over 3 gives me what? 5 pi over 3? So now I can fill in the rest. I can say this is the cosine of theta, which is 5 pi over 3 plus I times the sine of 5 pi over 3. And there is this complex number in polar form. How about part B? B. B is in boy. All right, so if I want to look at part B, I'm going to be looking at negative 28 minus 45i. All right, so let's find r first. R is equal to the square root of a squared plus b squared, right? So r is equal to the square root of a squared plus b squared. What's a? Negative 28. What's b? Negative 45, right? So I get r is equal to, I can't do this one in my head. I got the square root of 2809, and that actually ends up being a perfect square. That ends up being 53, okay? So I found r. Let's find theta now. To find theta, I want to draw me a picture first. I want to plot this complex number in a rectangular coordinate system. So where is it at? Negative 28 minus 45i is somewhere down here, right? Okay? Now think about whenever I find theta. What I'm finding whenever I find theta using the tangent of theta is equal to b over a is I'm actually finding this little acute angle each time, okay? So in this case, I'll be finding a reference angle right here, theta prime. So I'm going to say the tangent of theta prime is equal to b over a, which is negative 45 over negative 28. Oh, well, that'll be a positive, right? So tangent of theta prime is equal to 45 over 28. And can you simplify that one? I don't think so, right? No, if I look back, I cannot simplify that one. So what is theta prime going to be? Which angle has a tangent that's 45 over 28? Well, none of the ones I learned on the unit circle, right? So I'm going to say theta prime is the inverse tangent of 45 over 28, or the arc tangent. So this theta prime right here ends up being what? Inverse tangent of 45 over 28 is my theta prime. Now, which angle do I actually want? The angle that I actually want is this angle right here, right? How do I find that angle? I go pi plus theta prime more, right? So theta, instead of theta prime, will be pi plus theta prime more. So theta will be pi plus, what was theta prime? The inverse tangent of 45 over 28.
You go right or left?
So now, if I'm going to write this in complex polar form, I'm going to write it as r times the cosine of theta plus I times the sine of theta. Well, let's fill in now. So what do we have? What is r? R we found to be 53 times the cosine of theta. Theta is all this value, so I'm going to put all that in there. Cosine of pi plus inverse tangent of 45 over 28 plus I times the sine of this theta, which is pi plus the inverse tangent of 45 over 28. There we go. That's that number in complex polar form.